Okay, so my presentation as a whole is about calibration, and particularly about calibration of classifiers. Not just deep neural networks, but any classifiers, and deep neural networks in particular. So what is calibration? Calibration is basically the reliability of your probability predictions. So when you solve a classification problem, you get a data set, x's and y's, and you make predictions for each x. You make predictions with probabilities for each class, right? So the notion of calibration is about how close are your predictions to actual probabilities. Because when you are predicting something, you're predicting basically probability of an event. And calibration is about how close your predicted probability of an event is to the actual probability of an event. And it's not just defined for classification, it's also relevant for regression problems. So like traditionally when you do regression with deep neural networks, for example, you output a point estimate, but you can alternatively output a whole distribution of some variable, and then you can also quantify, like try to quantify how close or how distant your probability distribution is from the actual probability distribution. And I have to mention from the start that everything I'm talking about is not my work, but it's kind of related to my work. And I only recently started to read about this stuff, maybe 2 or 3 months ago. And I got interested in it because I think that reliability of machine learning systems is important in a broad sense, right? So in particular, the reliability is important in the safety critical systems. In systems where you solve some kind of problem, like classification problem, and you really need all your probabilities to be right. So, like for example, you predict a like whether you have cancer or not, and you also predict probabilities of various types of cancer. And in addition to predicting, in addition to your most likely type of cancer that you predicted being right, you also need all your probabilities to be right, because like there are benign types of cancer and types that are not so benign, and this is relevant to self-driving systems and etc. And in addition to that, like the second use case of calibration, even if you are not concerned with the reliability of your predictions, you may still want your model to be calibrated. For example, when you do model selection, or like for any kind of downstream tasks. When you do model-based reinforcement learning, for example, you want your model to be calibrated to benefit from it during the reinforcement learning process. Yeah, and this is basically relevant to our work that we did with Dmitry Molchanov, Dmitry Vetrov, Arseniy Ashukha, and Yulia Molchanova. And we investigated first whether you need calibrated models for model selection when you select policies of augmentations of images when you do image classification. You can augment images in some kind of way, in a learnable way, and we found that your model has to actually be calibrated in order to select the right types of image transformations. And in addition to that, calibration can be important in other downstream tasks, distillation, etc. And we also found that ensembles of neural networks, which are traditionally thought of as calibrated are actually not calibrated, and it can be easily fixed. If you try to solve a classification problem with your deep neural network, chances are that it is not calibrated in some way, and the probabilities are not exactly what you want them to, even if it seems like you don't have overfitting. Okay, this is in contrast to deep neural networks of 90s. Like for example, if you take LeNet, that was introduced in '98, I think, and you take ResNet, which was introduced in 2015, and measure the calibration error in some way, or like the discrepancy between probabilities that you predicted and the actual probabilities, then it turns out that even though ResNet's accuracy is much better than networks of 90s, it is not as calibrated. Okay. So let's dive in, and this is an overview of my talk. I'll first go through the various definitions of what it means for a model to be calibrated when you solve a classification problem. And this is not straightforward, because you can actually define the discrepancy between your predicted probabilities and actual probabilities in various ways. And after you define this discrepancy, you can try to estimate it based on data in some way. And I'll talk about estimators that each have different properties, and some of them are more preferable than others. I'll talk about results of application of these estimators to deep neural networks. And if I have time, I also want to talk about the methods of making your neural network calibrated. Like you can do it during training. Like you can ensure that your network is calibrated during training. And you can also train your model and then try to ensure that it is calibrated. But the main part of my talk will be about measuring calibration versus ensuring calibration, because it seems to me that measuring calibration is a maybe more fundamental, because once you know how to measure it, you can then try to optimize the metric that you've got. So these are maybe the three main three main definitions of perfect calibration, which we may think of. And here g of x determines our model, for example, a neural network. The inputs x and outputs a probability vector of probabilities of various classes. And the first definition is about, it is called confidence calibration. And what it intuitively means is that if you make some kind of prediction, you got this vector of probabilities, and on the condition of your confidence of your calibration, or your maximum element in this vector of probabilities having a certain value, then the probability of the class which you predicted as correct is equal to that value. So this is what the first definition says. The second definition is about calibration of all classes, and not just the class which you predicted as correct. So like on the event that you predicted a certain class, the probability of that class will be equal to the predicted probability for that class. And finally, we can also define the joint calibration, which is basically on the event that you predicted the whole vector of probabilities, the actual probabilities of classes will be equal to the vector that you predicted. And I'll go through examples to make these definitions more clear, and basically provide counterexamples that that show you that your model can be calibrated this way, but not the other way. So, yeah, if your model is confidence calibrated, which is if the class that you predicted as correct is always calibrated, it doesn't mean that all classes are calibrated. And even if these two definitions are satisfied, it doesn't mean that the whole vector of probabilities that you predicted is calibrated jointly.
Why?
Let's see. So the first two definitions. This is a table with rows corresponding to events happening with equal probabilities. So like probability of 1/2 this happens, probability of 1/2 this happens. And with probability of 1/2 you predict this vector of probabilities, like you have 3 classes, and the actual probabilities are as follows. And the second row basically is the same. And here you can see that your model g of x is confidence calibrated, which means that on average, when you predict, when you make a prediction and the maximum of your prediction takes a certain value, then on average the on average the probability of the class that you predicted is equal to that value. So here it's 60%, and here if you average the probabilities of the classes which you predicted, you also get 60%. Okay, but as you can see, so for example, we predict this vector of probabilities, and 60% is not equal to 70% in this case. So like, if we take the first row, this conditioning on g of x is happening on this whole vector. And
what is x large? Is it a single object or is it a set of objects?
Here it doesn't matter. So it can be a set of objects. This is a random variable, okay? And we can have one object like this and one object like this, or we can have multiple objects like this and multiple objects like this.
Okay, but then how to interpret the definition of calibration of the first type, confidence? I still do not understand. So we have a set of objects, x large, right?
Yeah.
For each object you find the maximum probability, and you condition on that probability.
Yeah, so you look for all rows in the second column which have maximum probability equal to the value. So for example, to 60%. And these two rows both have predicted maximum probability of 60%. Okay, so you take them both and you try to find the probability of the class that you predicted in all these cases. You average it out, and it is equal to 60%. Yeah, but...
So this is a kind of integral measure. Not related with a single object, but related with a set of objects. And on average, there should be equality.
Yeah, so here you look at the probability of a class on a whole set of objects for which you predicted this vector, or this maximum value, okay? So this is kind of an example where this is satisfied and this is not satisfied.
These equalities should be satisfied for all possible x's?
Yes, for all possible x's. Or for...
On average, not for all possible x's.
For all possible g of x, let's say. For all possible predictions of your model. Or for all possible maximum values, okay?
So basically, in your definition, you should put an expectation over x before the left and the right parts. Is this correct? You should take an expectation over x. Is that what you're saying?
But the probability is already an expectation of indicators. right?
So this is a probability for a given x.
And the conditional probability.
Yeah. So from this definition, it seems like we take an object x, and then we calculate all the probabilities for this object.
We need the probability of holding this equality, for example.
Well, if we make this definition longer, we can write here that maximum of the predicted vector of probabilities is equal to some value and conditional on this event. Then it will be right, I think.
No, you agree that both parts are dependent on x large. So they're still random variables because they're functions of x large. And you need to average with respect to all possible values of x large. This is what guys I advise you to do.
Yeah, but if you do like I said and write here like maximum equal to some value, then you can already like average x's out implicitly, because if you take this whole event, then it will sort out x's that satisfy this condition and x's that do not satisfy this condition. But I think it's just a matter of notation, right?
Okay.
So I'll return to this. And also we can say that even if the first two definitions are satisfied, the joint calibration definition is not satisfied. Let's try to see this. So here, let's just look at the first row and single out those vectors of probabilities that are equal to like those that have an element in the first row equal to some value, for example 10%, and average all corresponding entries in the second column out. So like for each such value we get the average the probability of an event equal to the predicted probability. Yeah, but if we condition on the event that we predicted this vector, we will not get the actual vector of probabilities equal to what we predicted it.
And if we average out with respect to all such objects which would have the same prediction and compare it with the two predictions. Because again, you should still have an expectation with respect to x large, and you should average the results with respect to those x's whose g of x has the given value, because this is your condition.
Not really, because like here in the right part, this g of x is not actually some function of x. It is some value, like for example, you could write here not g of x, but some value rho, for example, and then write rho on the right half, and on the left half, as Sasha said, write g of x equal to rho. And that will select you a subset of x's that provide you with the probability rho.
Right.
And then you can define this probability, like of y is equal to y.
Yeah, that would be.
So you would not need to average over x, because you need x to define this probability.
That would be much more clear.
Yeah.
What you say, what's on this side.
Okay. And this is an example showing that even if you have the strongest calibration satisfied, your model still can just output random probabilities, right? So like in this example, for all x's, the models outputs like 50% and 50% of two classes, and the actual values of probabilities for these two objects are entirely different. But if you average all x's that you predicted this vector on out, you'll get the average equal to your predicted vector of probabilities. So this means that you've got to care about both accuracy of your model and measures of calibration, on the other hand. Now let's look at how can we quantify the discrepancy. Like if your model is not perfectly calibrated, you've got to somehow measure the like how miscalibrated is it. And here I define R of xi, which is a vector of probabilities conditioned on your model predicting a certain value xi. Okay, a certain vector xi. And joint calibration again means that this predicted vector is equal to the actual probabilities of your classes. And this R is called the calibration function. Or
probabilities of all objects for which we had the same prediction and we have averaged the two values. And after averaging, we obtained exactly the same vector probabilities.
Yeah. Yeah, this is called a calibration function, or alternatively canonical calibration function in literature. And with this notation, we can define calibration errors. So these are not estimates; these are like expected calibration errors. And I'll discuss estimates based on data later. But here you can see that we can introduce some kind of distance between this vector and this vector, which may be total variation distance, or L1 or L2, some kind of distance. And we can average it out, which results in expected calibration error, or EC. And we can take the largest distance out of all possibilities, which results in maximum calibration error, or MCE. And it should be easy to show that in the case of joint calibration, both these errors are 0, right? Because the distance is 0, and vice versa.
And expectation as a term is with respect to xi?
It's with respect to your data x, for example, x and y.
That's correct. That if I take like a model which outputs a constant prediction with the probabilities of the classes, like just I can return the same numbers, it's perfectly calibrated.
So in this example, yes, maybe not always, but yeah, it can be perfectly calibrated.
If I just like output the rates of the classes,
Mm-hmm.
it has a joint calibration. It's stupid, but it has.
Oh, in some sense, this is ideal calibration.
Yeah,
it's absolutely useless, but it's perfect.
Okay.
But this example does not have MC equal to 0, because you can take x large equal to just x1 and see that the distance is not 0.
Again?
So here you have joint calibration, right? But if on the next slide you average over all possible x's, then here your MCE is not equal to 0.
Yeah, MCE. Let's see. So the supremum between. So MCE depends on D, right?
Yeah.
What is D in this case?
Anything like L2, for example.
Mm-hmm. So like the distance between left-hand side and right-hand side in the left table.
In the not in the
We
right.
are not computing calibration error with respect to single objects. We are computing calibration error with respect to the set of objects for which we have the same predictions.
Right, but then what is the x on the next slide? When you take the expectation over x, what does it mean?
Yeah, well, I think it's ordinary to say that we're taking expectation with respect to psi.
Well, I
With
thought
respect
so.
to different predictions.
Yeah, I thought so, but I asked about it and said.
I think that there was a kind of misunderstanding.
Mm.
So the expectation is, well, it is computed with respect to x, but in the sense that actually it's computed with respect to psi. Because all objects for which we have the same prediction are treated equally. So we average their statistics.
So we can say that it's.
We may say that we factorize the set of objects with respect to.
Yeah, I understand, but I just want to clarify: is this the case, or do we understand it wrong?
No, the distance is 0.
So yeah, you can say that this expectation is basically with regard to xi.
Okay.
Sure. So here, like you have your model G, but like you want to use these errors to see if your model is calibrated or not, but you can't just do it because you don't know R. And R is basically a function that maps from your predictions to perfect predictions in terms of strong calibration. Okay. So I'll basically talk about two main methods to measure these two errors. And the first is histogram.
Wait a moment. Why don't we know the function R? It seems that everything is computable there. We have training set. We can factorize all objects with respect to the predictions by our model, and then we can.
We have a finite training set and a finite testing or validation set. So we can compute the empirical frequencies, and this is what I'll be talking about here in histogram regression calibration estimator. So yeah, the first type is histogram regression, which is what you are talking about. And the second type, the more sophisticated type, is based on so it's called maximum mean calibration error. It's similar to maximum mean discrepancy, which you use to distinguish two distributions. So first I will talk about this one. For example, like again, you have a multi-class classification and you have a simplex, which your vector of predicted probabilities takes values in. You can partition it somehow. You can have an arbitrary partition of this simplex. For example, you can do a uniform partition into like chunks of the same size. And you can approximate this function R of xi with the empirical frequencies. So conditional on your model taking, it's like conditional on your model on a particular object outputting a vector of probabilities that is in a fixed partition on that simplex. And B denotes a partition here, like one partition. Yeah, so this estimate is the number of times you got it right in this bin versus the number of times that your prediction fell into the bin. Yeah, and this is with regard to a specific y. So to get an estimate for the whole R of xi, you would take the whole vector for all y's. So the ECE is basically approximable with such an expression, where you take a sum overall of your bins of the simplex. You weigh the bins according to the number of objects in each bin, and NB is number of objects in a bin B, and N large is the total number of objects. And then you compute the average difference or average distance d between average distance between what you predicted on objects x. So this sum, it's written b here, but it's x in b. So this sum is with regard to all objects in the bin, and you take a difference between what you predicted on average and what are the actual probabilities on average. So this is a visualization to help you better understand this estimator, and it's from a paper on model calibration in deep learning or something like that from 2017. And here, so I won't talk about the upper side because we don't have time for that. But let's look at the lower part of the slide. And on the left, we have what's called a calibration diagram for LeanNet neural network. And on the right, we have a calibration diagram for ResNet. And here we solve a binary classification problem. So we have positive class and negative class. We leave the negative class out and partition the one-dimensional simplex that we get. So like we predict a probability of positive class, and then this probability falls into one of these bins, which we partition the one-dimensional simplex on. And here we have 10 bins, right? So for each bin, we can plot the average of, let's see, the average of your predicted probability for the positive class. So on the event that your predicted probability falls into this bin. And you can see here that for LeanNet, on average, your predicted probability is in line with the actual probability of the class. But here, the probability that you predict is different in each bin.
And how do we get binary classification problem from CIFAR 100?
Oh, yeah, I have to talk about this. So this is this ECE. Right, so we have ECE here, and we define kind of. So we have a multi-class classification problem, but we can define an induced model G and induced calibration function R, such that an induced problem X and Y, such that we actually measure the discrepancy between left-hand side and right-hand side here. And basically, if we only care about whether the maximum predicted probability is right, we get an induced binary classification problem. So if we look at this, at these calibration diagrams again, this is probability of the largest class that we predict, like largest probability of the class that we predicted, regardless of the class. This could be any class. And yeah, and on the y-axis is the actual probability of this class conditioned on us predicting a vector like falling into some bin, and like average of our predicted probabilities for the class, which is the class that we predicted, basically.
So doesn't it mean that the ResNet could be better on the joint measure of calibration? So here you see that ResNet is better on predicting the maximum probability. Okay,
yeah, I get what you ask. Basically, so when you measure the discrepancy like this is one value. Like you measure the discrepancy, you get one value. And you measure the discrepancy of, like in the sense of joint calibration, you get another value. And these two values are not really comparable with each other. So we can't say that it's better calibrated jointly than its maximum probability is calibrated. But we can say for sure that if it is not confidence calibrated, if our model is not confidence calibrated, then it cannot be jointly calibrated. But how much is, depends on how you measure it. This is a very similar thing, but for multi-class classification. So this is for CIFAR 10, actually, and this measures joint calibration directly instead of confidence calibration. So here you have like groups of classes for convenience of visualization. And this is a simplex, a two-dimensional simplex. We can partition it into bins of fixed size the same way and represent deviations with arrows. So for each bin, this could be the average of our predictions, and this could be the actual probabilities on the simplex. So this is just a visualization tool that was introduced last year.
How can you make sense of the errors?
Well, like consider this bin. Okay, and like for example, the arrow tail is here, right? Right near the corner of the simplex. But the arrow head points into the center of the simplex. And if you get that, that would mean that for this particular group of classes, you would be better off predicting less confidently.
Yeah, but
basically.
the size of the errors is negligibly small. Does it mean that the model is more or less calibrated?
This is for LeNet, so yeah. Mm-hmm. But if you look at this diagram for ResNet, you would get errors all over the place.
So we may take the total length of all errors, or the average length of the error as a measure of miscalibration.
Yeah, and this is what you get when you apply the estimator below.
Why is it good if, like on the previous slides, the distribution is around the diagonal of the square?
This would mean that, like for example, let's take the largest bin, and in the largest bin, if you predict probabilities that are fall into this bin, they are high confidence predictions. Okay, for any class, and
may I try to explain? Let's consider the bin which corresponds, say, to 0.6. This means that the model says this object belongs to the given class with a probability of 0.6. And if the model is calibrated right, it will mean that the model will make a mistake in 40% of the cases. And in 60% of the cases, it will be right. And this is exactly what we expect if we see that the model is 60% sure that the object belongs to the given class. So if there are more objects that belong to this class, then the probability of the model should be higher. If there's less objects which belong to the if there are less correctly classified objects, then the probability should be less. This is why they should be kind of diagonal. So if the model is 60% sure, it should make 60% of correct answers. Not 70, not 50. This means that the model is perfectly calibrated.
Yeah, I may have been mistaken because I described blue bars as average of model predictions, like the largest model predictions. But here it seems that blue bars denote the empirical frequency of the largest class. And from this you can see that in many cases you would actually be better off on average if you predicted less confidently. Then the objects that predictions for which fall into this bin with the highest confidence would move left, and then then the predicted probabilities would align with what we got here. Let's discuss some properties of this estimator briefly. So it's called Histogram Regression estimator because you construct a kind of histogram on the simplex, like histograms of how much do you get the predicted class right. And you try to make your model kind of solve the regression problem in some sense to like for the average of your predicted probabilities to be equal to this. This can be viewed as kind of a regression problem. So what's on this slide? So what does this mean? This is our estimator of the joint calibration of this model G. And let's suppose that we take the infinite sample size limit, and suppose that we partition our simplex in such a way that that the bins are smaller and smaller, and in the end, the area of each bin is infinitesimally small. Then what we get is our EC estimate is actually equal to the expected calibration error itself, like with the true probabilities of classes. But of course, we cannot reach this with real data because we don't have this infinite sample size. And additionally, even like for a fixed partition, not for a partition with very, very small bins, but for some fixed partition, if we fix it and make the sample size go to infinity, then our estimator will actually be a lower bound on the expected calibration error, which means that it is biased. And these are the various things that you can say about this estimator. So for one model G, you can get one bias here, like one difference between ECE and your estimate. Disregard this part. But for another model, you can get a different bias. So if you compare the values of your estimator for different models, you cannot be sure whether you are measuring calibration error or whether you are measuring bias, actually, bias of your estimator. Yep. In addition to that, so like when you resample your data, you get different values of ECE estimate, and you don't really take the whole range of values, the whole distribution of values into account. You just have a single estimate, which you somehow should make sense of.
And what do you mean by resampling data?
Well, if you have
another training set?
Yeah, synthetically, for example.
Okay.
Just like a thought experiment.
Or maybe more training, maybe just validation also. Yeah. So I don't think it makes much sense to measure expected calibration error on a training set.
Yeah, you could measure it on calibration and resample the calibration too. So, yeah, this is an example of a bias that I mentioned in this estimate of expected calibration error. So let's suppose that we have some kind of data set with classes taking equal probabilities over the data set. And let's also ensure that the data is clearly separable. Like there's no uncertainty in the data about the class label. And we can think of two models, G optimal and G constant. G constant just predicts equal probabilities of classes. G optimal predicts the true probabilities. So for both,
but those probabilities are not dependent on X, right? Or they are.
Here, they should depend on X. This is a mistake. Both of these models have expected calibration error of 0, but if you compute the expectation of your estimate for optimal model, you'll get 0 because the probabilities that you predict are always equal to the true probabilities. Okay, And for the second one, it will not be 0.
Excuse me, do you have 2 classes or 3? Because I
this is for 2 classes.
So
yeah,
the
so
first,
the negative
one
and positive.
is actually equals to 0 and to 1, yes?
The class for x can be equal to 0 or to 1. Yeah.
I mean, the first line, it says like y could be 2.
Ah. Okay, 0 or 1.
And the worst thing about this metric is that it is commonplace in all the papers. Like there are dozens of papers that use it as one of the main metrics for evaluation.
Yeah, so if we look at this estimator, it has all these pathologies, let's say, but all of the papers just use this estimator, and in addition, they use it for estimation of confidence calibration error, and not joint calibration error, and not marginal calibration error. Not all of papers, but most of them, in any case. So this is a series of slides about an alternative way in which you can measure calibration error instead of using that histogram regression estimator. So instead of defining ECE, like it was defined before in this way, we can define it for some kind of functional class f large as a supremum over all functions in this class of the expected difference times the value of this function on the predictions of your model. So this can be thought of as maybe discriminator functions that try to judge, try to discriminate the actual probabilities from your predicted probabilities based on your predicted probabilities. Okay? And if we have joint calibration, obviously this is 0 because the first term inside the expectation is 0. If we have calibration error equal to 0, this is does not necessarily result in joint calibration of G, because you can pick a functional class and provide a counterexample. But like if you pick a functional class consisting of continuous functions which map from your predictions on the simplex delta m to real valued vectors of the same dimension as this vector, then if we have this calibration error equal to 0, we will have joint calibration. But it turns out that this functional class is kind of useless, because in this case the calibration error is either 0 or infinity. Yeah. So you can't really tell apart the different models. So what do we use in this case? We may define a functional class with a kernel. And this is a set of definitions for one-dimensional case. So we can define some kind of kernel which maps from a set of objects times set of objects to a real value. And if this function satisfies these conditions, symmetricity and positive semi-definiteness, then there is a unique functional space which corresponds to this kernel. And it is called reproducing kernel Hilbert space. And in reverse, if we have a Hilbert space which satisfies this mild condition, it doesn't really matter what it is, then we have a unique kernel which we can map, which corresponds to the functional class. And why is it called reproducing? Because if we take a kernel corresponding to the functional class h, then the kernel kind of reproduces the function, because if you take a scalar product of kernel and function with kernel with a specified point, you'll get the value of your function f at the point. And what I want to show here is the same construction, but for multidimensional case, which the same theory holds for multidimensional case, but the kernel here actually maps from the Descartes product of simplexes to a matrix. This is why it's called matrix valued kernel. Same conditions, same reproduced property. So why do we define all this? Because we want to define this function class f somehow. And in addition, we want to compute estimates of this calibration error easily. And with RKHS, we can actually do this. So let's define some kernel which satisfies these requirements from the previous slide. Like very simple kernels, Gaussian kernels satisfy these requirements. And let's define kernel calibration error with respect to a kernel G, which maps something to a matrix, as calibration error or with a functional class that is a unit ball in the Hilbert space defined by this K, corresponding to this K.
Am I right that you said that the f is the function from the simplex to a scalar?
Here,
No, previously.
This f, right?
Previous.
From previous slide.
Oh, okay.
So in some sense, we're trying to restrict the norm of a function. Because if we have no restrictions, it would take just arbitrary function which is continuous. Then we take either 0 or plus infinity. And in order to get some meaningful values, we need to somehow restrict the norm. And this is one of the possible cases.
Yeah, we cannot allow the function to grow arbitrarily fast. We need to restrict the growth somehow. This is why we define the functional class.
And those of you who are familiar with, say, Wasserstein guns may easily notice that the same idea is exploited there. We somehow restrict the flexibility of our function class in order to avoid of getting functions which are oscillating, which change too fast, right? And one of the ways, not the only one, not the unique way. So there are many ways of how we could restrict. For example, we could establish a kind of Lipschitzness of a function. But one of the possible ways is to restrict the functional class by saying that we'll take only functions from reproducing kernel Hilbert spaces and consider unit ball in this space.
Yeah, and this
case, Lipschitz assumptions would not work because it gives you restrictions on the derivative and not on the function itself. So if you say that your function is just Lipschitz, you are not able to satisfy the restriction on the norm. Restriction on this.
I understand. CE. Yeah, but for example, in GANs, there are many formulations where the derivative is important, not the absolute values of the function itself. But the idea is the same. We somehow restrict the functional class in order to get rid of plus infinities.
Yeah, and in addition, defining the functional class this way turns out to be very convenient because we can just we can prove these two things. First, that we have joint calibration if and only if kernel calibration error is 0 with mild conditions on the kernel K. So if kernel K satisfies some mild conditions, we can guarantee this. And in addition, with some mild conditions, we can guarantee this as well. And this is this turns the calibration error defined as like a solution of infinite dimensional optimization problem with regard to f to just a single expectation where we have our model G and kernel K, and that's it. And this expectation, by the way, is with regard to x and y and x prime and y prime. And here x and y and x prime and y prime are independent instantiations sampled from our data set, like from validation, for example. And what's important here is that there is no R here. We don't know R, but we know our kernel K. So we can just compute estimators of this quantity.
And what is E?
Oh, sorry.
Basis vector?
E is a one-hot vector corresponding to Y. So on a position of class Y, there is 1. On other positions, there are zeros. So this expression is kind of similar to the to Breyer score, maybe. If you remove the kernel, and if you just take this with x and y and this with x and y, and take this dot product, then you'll get something very similar to the Breyer score. But here you do it with one object and a different object.
And do you understand the geometric intuition of the kernel matrix in the middle? Why do we use it? What does it give us?
It gives us a functional class. Basically, it defines a similarity between predictions, like prediction on one object and prediction on another object. We can measure similarity of these predictions.
And so, in some sense, we managed to solve this functional optimization problem in the closed form?
Yeah.
There's no problem here, right?
Yeah. In closed form. So there's a long derivation, but we can get from here to here.
If we restrict our functional class to the unit ball in the reproducing kernel of the space.
Yes, I'll give examples of K. Let's go next. So we have this quantification of the calibration error, right? And now we can introduce, like, authors introduce various estimators for this quantity and prove various properties of these estimators.
Could you please repeat again, why do we have now like x and x prime? Is x an object or a data set?
Yeah, sure. So here we had expectation with regard to objects in our data set, x. And x and y, because R is also dependent on the data set. But here, this expectation is just defined with regard to x and x prime and y prime. And and x and y is distributed according to the generating distribution of our data set, and x prime and y prime is distributed in the same manner. And these two pairs of random variables are independent of each other.
Is y one-dimensional here or multi-dimensional?
Well, here y is a class label, and it's just it can be a number from 1 to n, for example. And this number is mapped into a one-hot vector, and we take a difference of one hot vector and our prediction. So it turns out that this KCE quantity is easily estimated. And first, this estimator was introduced in one paper. And it can be proven that it has a bias in the same way estimator of expected calibration error had bias. So you basically you take a number of examples from your data set or a mini batch, and then you how do you estimate this expectation? You get all pairs of objects in your mini batch and iterate over all pairs and just compute this quantity. So you have predictions of your model, you compute the kernel value, and you compute these things. So it's all easily computable. And if you take some if you take the sum in the estimator in a slightly different way than just all pairs of objects, then you can prove that it's an unbiased estimator of KC, and in turn an unbiased estimator of CE.
Can you give a bit more intuition why the first one is best?
The first one, like
counting?
this one, right?
Yeah.
It's not actually best. It's just
Biased.
Ah.
Biased is best.
I don't have a proof, honestly.
Oh, but the only difference between the first and the second line in the table is that in the first line we have double counting. So we have symmetric matrix, and we double count the elements there.
Here we also, yeah.
And in the second case, we take the summation with respect to just lower triangle.
Yeah, and in the second sum, we also do not include I equal to j,
Yeah.
the diagonal.
Yeah.
The matrix is symmetric because the kernel is symmetrical. Yes.
And the kernel is symmetric.
Matrix. Yeah, matrix is symmetric because of the symmetricity of kernel. So I don't have any intuition for why the second one is unbiased.
Well, it seems like in the definition of PCE, you should have a condition that x, y, and x prime, y prime are not equal. And then the second and third estimators are unbiased, and the first is biased. Otherwise, we have the opposite. So, in your expectation, x and y, x prime, y prime, should not equal, it seems.
I think that the probability that x equals to x prime is 0 if we consider infinitely large samples, but it is not 0 if we consider finite samples. And due to this effect, it causes bias. And if we avoid summing up the elements from the main diagonal, we remove this bias. I think this is the reason.
Yeah, essentially.
Also, I have another question. So, do I understand correctly that the second two rows are unbiased, not in the sense that they are unbiased estimates of TC per se, but they're unbiased estimates, like they're squared, like S TCE squared is unbiased estimate of TCE squared.
Right, yeah. So this is SKC. It means squared kernel calibration error, and this is defined with a square root. So yeah, this quantity is an estimate of this expectation, and all these estimators are consistent, which means that as you increase the sample size to 0, they are all converging to the value of KCE, even though the first one is biased. But
can you give some intuition about the third line? How can we reduce the complexity from square to linear?
I have no intuition, sorry.
Basically, I think you divide the data set in half, and you only take x from one half and expand on the other half.
Right.
But in their experiments, they show that the variance of this estimator is far lower. So
sure. If we divide our validation set by half, we'll take we'll obtain the reduced computational complexity. We'll keep the unbiasedness property, but at the expense of growth of variance. Right.
Yeah. So in practice, maybe it's a good idea to use the second one.
So that depends on the value of n.
Yeah. And the good thing about these estimators is that I think that when you train your model G, you can potentially just backpropagate through your estimators on a mini batch. So this was done with the first, just with the first estimator, and just for confidence calibration. But I think that you can potentially do it for marginal calibration and for joint calibration, and in an unbiased manner, while training your model, so that like when you have already trained it, it will be calibrated based on based on calibration error defined like this. So these are the empirical results of the guys from Sweden that introduced these three estimators. They basically synthesize three datasets and take different kinds of synthetic models for these datasets. So the model for the first dataset is unbiased, but models for dataset M2 and dataset M3 are biased. It's about calibration. So here the model is not calibrated in the sense of joint calibration, and here the model is calibrated jointly, and here the model is not calibrated jointly. So the kernel they use is they take x and y, which are model predictions, and they take the total variation distance, and then they apply a simple heuristic for tuning this single parameter. And when they have this measure of closeness between two predictions, then they multiply it by an identity matrix. So this is, in effect, a scalar kernel multiplied by an identity matrix, which means that it works equally for all classes. So what's depicted here is estimator of expected calibration error, biased estimator of squared kernel calibration error, and unbiased estimator of the squared kernel calibration error. And here the dotted blue line shows the actual value of calibration error, and this is an average of estimates taken by resampling the synthetic dataset multiple times. So like a few dozens of thousand times. And you can see that everywhere except for the third row, you get the bias between the actual value of calibration error and your estimate. But yeah, in the third row, they align. And for expected calibration error, the bias you get with a finite sample can be both negative and positive. And it can be pretty huge. And this is about the experiment that they did with optimizing such an estimator during training of the model. So this is squared kernel calibration error estimator, which is biased. They used a biased estimator because unbiased estimators were not introduced back then. And they applied for confidence calibration. So this is a measure of the discrepancy between your predicted probability of the maximum class which you predicted, like maximum predicted probability for a class. And this refers to whether your prediction was correct or not. And they average these quantities over a mini batch of data of, say, 100 objects. So this does not take a large time to optimize, because here you just have 10,000 terms in the sum then.
And do I understand right that due to the fact that but the estimate is biased?
Yeah.
But if the estimate is biased, we, strictly speaking, can't use mini batch. So we could use mini batch in case we were sure that the estimate is unbiased.
Mm-hmm.
So if we switch our miscalibration error to mini batch, this means that we impose bias, right? So, strictly speaking, we're not optimizing the objective.
Yeah.
On the last line.
We are like approximately optimizing it, but not really. Mm-hmm. But despite this, it works. So what they do is they just optimize the cross entropy plus lambda calibration error, and this acts as a regularizer of sorts. And what they get is when they finish the training, they compare this MMC plus T, maximum mean calibration error plus T. This is the result of optimizing this objective. Baseline is the result of optimizing cross entropy. And baseline plus T, so plus T here refers to temperature scaling, which is a way of taking your model, which is uncalibrated, and turning it into a calibrated model. And they show that I'm not sure why I included this plot, because it ideally it should show that MMC versus baseline plus T, like the MMC works better.
Well, maybe it does a little bit better.
Yeah, so it seems like if you apply temperature scaling on top of optimizing this objective, it works better than if you would just optimize the cross entropy plus do this calibration thing after the training.
And what about this lambda? How do they tune it?
I think they tune it on the. They either tune it on validation or they just set it to a fixed value.
Does it depend on the size of a batch?
They just did experiments with fixed batch size.
And do they compute SKC on training data or on validation data?
This is on training data, I believe. Yes, this is all on training. So this is the end of the main part of my talk. Do we have like 5 to 10 more minutes?
5 to 10, yes.
Yeah, maybe 15. Okay, sure. I will not take long. So I want to highlight. So once we sorted out the ways we can measure calibration, now I want to highlight a few ways to make your model calibrated with respect to those measures we invented. And these two methods, histogram binning and isotonic regression, they are defined for binary classification, I believe, but they can just be extended to multi-class classification in a one versus all manner. Histogram binning refers to the procedure where you take your model, G, and you do the binning of the simplex again. Like for a problem with two classes, it is a one-dimensional simplex. You take, for example, 10 bins, and then for each bin you compute the average value of the probabilities of positive classes for all objects, predictions for which fall into this bin on the simplex. And then you change the evaluation procedure of your model by taking the predicted probabilities and turning them into average turning them into average occurrence of some class in this bin. This is what it does, and this is basically this a very similar thing, but here you also optimize the boundaries between bins A. And I believe isotonic refers to the property of the resulting model, that is, theta is non-decreasing over the bins. So like as you go towards higher bins with higher confidence, the probabilities that your model predicts do not decrease.
No, but I think the same holds true for the histogram binning.
Not necessarily, because you could take a bin and you could find this theta m, which is the actual class occurrence, and it could be lower than for the next bin, or like higher than for the next bin. It depends on what is the distribution of your predictions.
Okay.
And so yeah, so we have these two methods, and we can also do this in a Bayesian way. So like we could impose a prior on all possible binnings and marginalize with regard to binnings, and do the same thing, but with like binnings adaptive to the data. But no one actually uses these for deep neural networks, because it turns out that simple parametric ways of calibrating your model post hoc after it has been trained work equally well or better. And for multi-class, and they fit naturally in the multi-class setting. So here Z is the vector of your logits before softmax in your deep neural network. And then you could use a validation dataset to turn these two parameters to basically linearly transform your logits. And this approach is called plot scaling. And temperature scaling is the same thing, except that you do not train the bias, and you only train the basically the scalar diagonal of this matrix. And here you tune the single parameter for the whole model on the validation dataset. Which
isn't softmax invariant with respect to shifts?
It is invariant with if you like take Z plus A, then it is invariant. It is not invariant if you divide it by something, by some scalar. So if you do this temperature scaling, for example, it turns out that most deep neural networks which do classification actually greatly benefit from this procedure. So you could do training of a deep neural network classifier, and you track the test loss. The test loss decreases gradually, and even though it decreased along the whole training trajectory, after training you apply this method and you tune a single parameter, and the loss drops by a lot.
Excuse me, in plot scaling you actually don't need B, right? If softmax is invariant.
Sounds about right.
But it may be a vector and it will be many different numbers.
Yeah, if these components are different, then it is not invariant to this.
If B is a number, then
maybe,
we can just drop it. If it is a vector of different values, then we can drop it.
Okay.
Yeah, maybe. I'm not sure actually. So if we apply this procedure, it's very effective, as I said. But it was shown to be very effective for confidence calibration. And recently there was a paper on NeurIPS 2019, I believe, which showed that when you apply temperature scaling and measure some more sophisticated measure of calibration, for example, marginal calibration, then it doesn't do well for marginal calibration. And it has a few disadvantages in that it changes the confidence of your predictions uniformly. So like, even if you are legitimately very confident in some prediction, it still makes this prediction less confident, because there's only a single parameter to tune for the whole data set. And potentially we could do better. But for some reason, these two procedures work about the same in practice for confidence calibration. And the third final option which we can do is instead of training a model and then calibrating it, we could do it while training. So we could do the same thing I have already shown. We could add a regularizer, like SKCE, for example. We could also do a entropy regularization of the distribution that we predict right in the training process. And this was shown to be somehow equivalent to temperature scaling. Because temperature scaling can actually be derived using maximum entropy principle. And this is basically similar to temperature scaling, but applied during training. And like a week ago, a new paper came out that claimed that if you use a different loss instead of just maximizing the likelihood of your data, if you use a focal loss, which is defined in this way, so here G is your model. Sorry for this, I don't know what this is. Logarithm. Okay, this is logarithm. So if gamma is equal to 0, this is just log likelihood. But if it's, for example, 2, then this thing downscales the predictions you are already good at.
Can you plot the function? How does it look like?
I'm not sure. So
that's a bit strange because we penalize the large margins for the training objects, and there's evidence to suppose that the larger margin is the better generalization ability, even for deep neural networks.
This loss was originally introduced for object detection.
Yeah.
There is a problem with Fusion bounds between positive and negative objects. So the goal was not to focus on the objects which you already do well. Because then you try to push them further and further, and you are not focusing on the boundary.
Okay, but here's the opposite case. We can actually achieve zero training error, right? So we classify all training objects correctly. But we somehow prevented the deep neural network to have large margins for the training objects.
I'm not sure. Like for some objects which we already predict well, yeah, we downscale the loss. So we apply this weighting for all objects in the mini batch. And for some objects which we do not yet predict well, the margin can decrease potentially.
That's why I was asking to plot the function, because it's not obvious how it behaves. At least for me.
Yes. What are typical values for gamma in this loss?
2. It's I mean, yeah, it's typically 2.
What will happen if you try to train a neural network using just the previous bonus to your, just with the regularizer?
Like this?
Like on the previous slides, you had the cross entropy plus.
Yeah. So this is the first point here.
Oh, yeah.
This is the regularizer which we optimize.
I think the question was like, what would happen if we just get rid of the data from altogether and we just optimize the regularizer, right?
So this is a very good question. And I don't know about classification, but in case of regression calibration, they show that you can just optimize the regularizer, and it works really well.
Probably it is because in the regression you cannot match the probabilities of infinite number of classes. And in the classification, your method will just try to match the probabilities.
I'm not sure I understood you.
Like the optimum would be a model that outputs uniform predictions. Like the model that outputs uniform predictions would be perfectly calibrated, and therefore, like these calibration metrics would be 0.
So anyway, you need to establish a kind of compromise between accuracy and calibration. Okay, is that all?
Yeah, this is the final slide. I think. Oh, this is the final slide. All right. So there's a lot of open questions because this is just recently introduced. And in MMD, in maximum mean discrepancy, we know that the kernel matters a lot. And here it probably also matters a lot. And then the question is, how do we select it? And if we optimize the regularizer, can we somehow select the kernel hyperparameters for this optimization? And does this all actually help in practice? So in this paper with SKCE estimators, they introduced calibration tests, so like a hypothesis testing for whether a model is calibrated or not. And they like the only result that they got is they rejected the hypothesis of strong calibration for all neural networks. This is it. So, but I don't know if it actually helps. Like if these strong calibration error estimators actually help in some applications. And this analysis of influence of hyperparameters for calibration error, it was done for biased estimators, but not for unbiased estimators. So I don't know. This is it. Thank you.
Any more questions?
So you showed that. Excuse me. Yes, I'm here. So you showed that. I forgot the green calibration. How's it called? The confidence, right? Calibration. The confidence calibration does not imply the marginal calibration, and the marginal does not imply the joint calibration. But the opposite is right or not?
So if you have joint calibration, then you have both of the other calibration types. Yes. And but I don't know about the case. Like I don't know if marginal calibration implies confidence calibration. It may actually not be true.
Yeah, I also think so. Thank you.
Any more questions?
Can this possibly help with the problem of adversarial examples, for example, like in image classification, when we change a little bit of an image and like everything changes, can this help with this problem?
I think that if you somehow manage to optimize the strong calibration error in your training, then it could potentially help with adversarial defenses.
Okay, let us thank the speaker for an interesting talk.